Alright guys, today we're going to start talking about masses and heavy pulleys. When you've dealt with systems of masses and pulleys before, we've always considered the pulley to be massless, and so we ignored it with all of our equations. But now we're going to look at what we have to do when we deal with the rotational inertia of the pulley. So the first thing I'm going to do is draw a free body diagram here for my hanging mass, which is attached to a string which is wound around a disc pulley which has a fixed axis of rotation in its center. So as we can see, we have the weight of the mass pulling down on it, we have the tension in the string pulling up on it, and so since it's accelerating down, mg minus t will equal ma. But we also have to notice that that tension in the string is also going to pull down on the right hand side of our pulley. And so we're also going to have that tension causing the pulley to rotate. And for that, we have to write our equation that net torque equals I times alpha. So the net torque on the pulley is going to equal the moment of inertia of the pulley times its angular acceleration. So in this case, the torque produced by that tension is just going to be the tension times the radius of the disc. As we learned yesterday in class, the moment of inertia of a disc is 1/2 mr squared, and then we put our alpha back in there. Okay, so now what we have are two different equations for our system, but one of them is in terms of linear acceleration A, and the other one's in terms of angular acceleration alpha. And so to be able to solve our system, we're going to have to put those two in the same terms. So our options are that either A equals alpha times R, or alpha equals A divided by R. And so you can sub in either way you want. It really depends on which one you're going to want to solve for. Do you want to solve for A or do you want to solve for alpha? So let's solve this for the linear acceleration A. And so that's going to be TR equals 1/2 mr squared A over R. And when we do that, that's real nice because now all my R's cancel out from my equation. I'm able to substitute in A over R for that alpha because the linear motion of the hanging mass, the linear motion of the string, and the linear motion of the edge of the disc, the edge of the pulley, are all the same. And so the acceleration of that mass and the acceleration of a point on the edge of the pulley are the same, so alpha does equal A over R. Okay, so what I've done now is just simplify that equation to T equals 1/2 times big M, the mass of the disc, times A, and I'm going to sub that into my other equation, mg minus T equals ma, and I'm going to get mg minus 1/2 big Ma equals little ma. And then I'm just going to solve that equation for A. So I've solved that equation by moving both terms with A over to the right-hand side, factoring out the A and dividing. And I see that the acceleration of the hanging mass, which is also the string and the edge of the wheel, would be little mg divided by 1/2 big M plus little m. So if we gave ourselves some numbers here, so I've given myself numbers of a hanging mass of 1 kilogram, the mass of the disc is 4 kilograms, and the radius of the pulley is 0.25 meters. So if I plug those values in, I'll end up with 10 divided by 3, or 3 1/3 meters per second squared. Now once we've solved that, it'll be very easy to go back and solve for the tension if we need that, and also the angular acceleration if we need that. And we'll do that on the next page. Alright, so as we said, the hanging mass was 1 kilogram, the mass of our disc-shaped pulley is 5 kilograms, the radius of our disc-shaped pulley is 0.2 meters, and the acceleration that we already calculated for on the previous page was 3.33 meters per second squared. So if we want to know the tension in the string, now it would be very easy to plug into either equation and solve for that. And I apologize, the mass of the disc was 4 kilograms there. Okay, so we say we plug into either equation, we get a tension of 6.67 newtons, which is less than the weight of our hanging mass, which we would expect it to be in order for it to accelerate down. And then finally, if we needed the angular acceleration of the disc, then we can very simply just say that alpha is A divided by R, and so that would be 3.33 divided by the radius of the disc, which I messed that one up too, that was 0.25 meters. Okay, so 3.33 33 times 4, and that will give us our answer of 13.33 radians per second squared. Alright, so now we're going to look just at free body diagrams and equations for a couple other systems, and then you guys are going to have some problems to try. Alright, so here we have our old friend the Atwood machine, where we've got two hanging masses on either side of a fixed pulley. But this time our pulley is going to have mass, therefore it's going to have a rotational inertia. And we're going to model our pulley as a disc again with a mass big M and a radius big R. So first, let's assume that M2 is bigger than M1, which means that M1 should accelerate up, M2 should accelerate down, and of course then that would mean this pulley has to have an angular acceleration that's in the clockwise direction. So we'll start off with free body diagrams of our two hanging masses and the equations that go with those. Alright, so I've drawn the free body diagrams and written equations that should be very familiar to you. Since M1 is accelerating up, we'll do the force up minus the force down equals M1A. And since mass 2 is accelerating down, we'll do the force down minus the force up equals M2A. Then we're going to look at the forces producing torque on our disk. So, of course, if T is pulling up on M1, it must also be pulling down on the left-hand side of the disk. If T is pulling up on M2, it must also be pulling down on the right-hand side of the disk. So, if that is going to accelerate in a clockwise direction, then when I write my equation, net torque equals I alpha, then my net torque now is going to be T minus T times R, and then my I is 1/2 big M R squared, and then alpha. Now, you should notice a problem here. If this is going to have an angular acceleration in the clockwise direction, then it should have a net torque in the clockwise direction. And for that to be true, these two tensions cannot be equal. The tension on the right side, which we'll call T2, must be bigger than the tension on the left side, which we'll call T1. T2 has to be bigger than T1 in order to get that clockwise angular acceleration. So when you have a heavy pulley and a string passing over it, it's different than the problems you've done before where the tension's the same throughout the string. We're actually going to have a different tension on the two sides of the string, and we will have to go back and reflect that in every single one of our equations. And then we should be able to solve remembering that alpha is equal to A divided by R. Okay? So today, guys, you're going to have some problems dealing with masses and heavy pulleys. Set up your free body diagram. Write your translational acceleration equations. Your net force equals ma. Write your rotational acceleration equations. Your net torque equals I alpha. And then solve your system of equations. Good luck, and I'll see you tomorrow.